All right, sure. So I guess we can start. So thank you all for coming. I'm here to introduce gnark. It's a fast and efficient zero-knowledge proof library written in Go. So first, an overview of gnark. So what is gnark at a first glance? gnark is a fast, open source, zero-knowledge proof library written entirely in pure Go. It's licensed under Apache 2. Currently, we support the Groth 16 protocol. So, as described by the talk of Lawrence Kirk before, we plan to add more talks in the more protocols in the future, namely protocols that allows to have a universal trusted setup. In gnark, to write circuits, you use the APIs that we provide. So I'm going to discuss that a little bit later. It's not a DSL, it's an API. And gnark takes care of the rest. In particular, it solves a rank 1 constraint system. And of course, gnark exposes the standard zero-knowledge functions that we all know, so the setup, prove, and verify algorithms. We also come with a command line tool, so you just have to call gnark setup, gnark prove, and gnark verify. So in short, gnark enables a normal development cycle for zero-knowledge proof. And the hope is that the API will abstract away the complexity of zero-knowledge proofs that tend to confuse people. And we hope that gnark will enable flexible integration into complex solutions. All right, so first, what is a zero-knowledge proof? So I will not dwell on that too much. There was a talk by Lawrence Kirk earlier this morning that described it pretty well. I just want to remind you of a couple of important properties of zero-knowledge proofs. The first one is called computational integrity. So the idea here is that if Alice wants to prove to Bob that she knows the input X such that when given to a program or circuit P, it outputs Y, she will provide a proof, and if the proof is valid, it must be that the input is correct. That is, she cannot craft a fake proof, a proof that is valid, with an incorrect input. And also, one of the very powerful properties of gnark is that the cost for Bob to verify the proof is in fact much, much smaller to actually execute the program P itself. It's a very important property for scaling solution on Ethereum, and it is used for scaling solutions such as rollup, for instance. So this is computational integrity, and there is privacy, so I'm sure that everybody here knows what this is. So the idea here is that Bob is, when he verifies the proof and if the proof is valid, Bob is actually convinced that the execution and the input X that gives rise to Y is correct, but he learns nothing about X. So you have the notion of private input, in this example X, that is not known at all by the verifier. Of course, it is used for doing private transactions in Zcash, where you have to prove that you know the spending key of a given node. Okay, so now I'm going to describe a little bit more in detail the Groth 16 protocol, so the protocol that gnark supports. So in this protocol, you have three main algorithms, which are setup, prove, and verify. The setup phase, you have to do it once per circuit. Basically, you give to the setup a program or a circuit P, and it will spit out a proving key and a verification key. To prove a statement, so if Bob wants to prove a statement that he knows X such that when X is given to P, it gives rise to Y, he will call the proving algorithm. He will give to the proving algorithm the program or circuit P. He will give the private input X and the public input Y and the proving key. And this algorithm will spit out a proof. So concretely, it's just a short file. So it's very lightweight. And to verify a proof, Alice will call the verify algorithm on the program P and the claimed input Y. She will use a proof, so the short file, and the verification key. And basically, the verification procedure will output valid or invalid according to whether the proof is valid or not. Usually, so typically, the proving part is done off-chain. It requires a lot of work from the prover. And the verification part is done on-chain. Typically, for Zcash, for instance, it is part of the consensus protocol. You have to verify the zero-knowledge proofs to check that the chain is correct. Okay, so the architecture of gnark. So mainly, you have 3 layers in gnark. You have the front end, the rank 1 constraint system, and the backend. So the front end, it's a user-facing interface. To write a program, you will use the front end. So a program is a circuit. The idea of the front end is to convert a high-level statement. For instance, if you want to write a hash function, for instance, mimc function or Poseidon, you write it using our API, and gnark takes care of converting it into a rank 1 constraint system. So then, of course, you have the rank 1 constraint system itself. One of the features of gnark is that it solves automatically the rank 1 constraint. So a rank 1 constraint, it's just a set of constraints involving the variables in your circuit. The rank 1 constraint, the rank 1 name just means that it's a very specific kind of constraint. And then you have the backend. So the backend, you can, for the user, it's a black box. You can think of it as a zero-knowledge engine. So it's where there is all the heavy lifting, so elliptic curves implementation, and it's where the Groth 16 protocol is really implemented. Of course, it's a bottleneck for snarks. You want the backend to be as fast as possible. And of course, the front end, you need it to be as easy to use as possible. Okay, so in this snippet of code, this is an example of how to write a circuit in gnark. So here, it's a simple Go executable. So first, you have to create the constraint system object. So it's a circuit variable here. The second step is to define the input variables. So from the first slide, those are the X and Y, X being private in this case and Y being public. And then you specify the constraint system. In this case, it's a really stupid program. It's a cubic equation. So some of you might recognize this equation from an old blog post from Vitalik and his snark explainers. So to write this function, you just use our API. So basically, it provides the use of arithmetic function. So you can add, multiply, and force variables to be equal. And you do that using our API. So it's supposed to be really easy for a user. Optionally, you can serialize the circuit on disk. So it's what you do with the circuit.write. The .r1cs, you don't have to know anything about it. It's just the extension. It means rank 1 constraint system. And it's all serialized on disk, and gnark takes care of everything. Okay, so for the backend, as far as the backend is concerned, this is all the users need to know. All right, they don't know anything at all about the underlying protocol, nor the arithmetic libraries underlying gnark. So to set up, prove, and verify a circuit, you will just have to convert the circuit that was defined previously. You have to convert it into a rank 1 constraint system. So this is what I do in the first line. Then you have to declare the proving key and verification key. And then it's as simple as that. You just have to call the setup, the prove, and the verify algorithm. And this is the Groth 16 workflow. So as far as the backend is concerned, this is all the users need to know. Okay, so we also provide a command line tool. So again, it's nothing too fancy here. It's really simple. Just have to call gnark setup with a .r1cs file, so the file that we serialized before. It will spit out the the proving key and the verification key. So cubic.pk, cubic.vk. To prove a statement, you just have to call the proving algorithm. Again, it takes as input the serialized circuit, the proving key, and the input. So the input, it's just, currently it's a CSV file. It might change in the future, in which the user just specifies the input. The user has to specify the visibility of the input, if it's private or public input. It spit out a proof object. Concretely, it's just a very lightweight file. In case of Groth 16, it's just a file that is under 1 kilobyte. So it's really lightweight, and you can prove very, very huge statement. So it's very efficient.
Is it a binary file or a text file?
No, it's a binary file. Yeah. There's nothing private in the file. Actually, usually the proof goes on chain. You can open it, you can do whatever you want with it. There's nothing private in there. To verify a statement, you just have to call verify. You give the proof, the verification key, and the input. Just have to take care here. So gnark warns you if you give the private input, but in the input file, input.public file, you just give the public input. All right, you don't have to provide the private input for verifying a proof, and it outputs valid or invalid according to whether the proof is valid or not. So it's as simple as that. Okay, so a little bit more details about that. So as you noticed, to write a program or circuit, you use a constraint system object. Okay, it's where we expose our API, and it's where you can call the arithmetic functions. But actually, a circuit, it's just a set of constraints. It's not an executable, okay? And sometimes you want to debug the circuit. That is, you want to query the values of some intermediate variables into your circuit. To do this, we have a rank 1 constraint system object. All right. To create this constraint system object, you give it the previous object, the constraint system. And one of the features of gnark is that it automatically solves the constraint system. Okay, there are no non-deterministic variables. You don't need to provide any hint or clues to the solver to instantiate all the variables. And you can use this feature to debug a program. So you can query the value of an intermediate variable just to check if you didn't make any mistake, for instance. You can think of the R1CS as the internal representation, as what the internal representation of a program is for a compiler. Okay, so quick example. Again, it's a Go executable. Don't pay attention to the program itself. It's a silly program that doesn't do anything, really. In this case, like before, I create a circuit, all right? I create the constraint system by calling the API. So here I create a secret input. I give it the name exponent. I multiply it by 10, why not? I want to query the binary decomposition of the TMP variable, all right? The 5 list significant bits. And if I want to debug, that is to query the value of the last two significant bits, so B0 and B1, I just call the tag method. Okay, that takes as parameter a string. It's a name that you will give to the variable that you want to debug. Okay, then you just create the R1CS object from the circuit. Then you create the assignment. Basically, it consists just of giving a value of the secret or public input that you created. And then you call the solve method on the R1CS by giving it the input, and it automatically solves the constraint system. So it automatically instantiates all the variables, and you can query some intermediate variables that has been tagged. Okay. So here I call the inspect method. It outputs a map. And you can query the variables that you have tagged. So here B0 and B1, you can check that it is indeed equal to 0 and 1. And by default in gnark, it also outputs the private value, the input values of the user. Okay, so some of you might have used other zero-knowledge libraries before. And you know that one solution to build constraint system is to actually create your own DSL. That is a subset of a programming language. We specifically chose not to do that. Instead, we have chosen to create an API for several reasons. First, it allows us to leverage all the nice features of Go, because we think that Go is a sufficiently mature and widely used language which provides a robust toolchain. Using defining a circuit using an API, it allows users to debug, test, and benchmark their program, actually as they would do with any normal Go program. You can version and unit test your program, and you can work in a standard continuous integration workflow. Also, the fact that we expose our own API, it allows gnark to be very flexible and to be very easily integrated to complex solutions. Okay, so I claim that gnark is fast, but how fast it is really? To do those benchmarks, we commissioned an AWS instance of 96 CPUs, 192 gigabytes of RAM. And we compare it against Bellman, which is a state-of-the-art zero-knowledge proof Groth 16 implementation. So it's logical to compare ourselves via this state-of-the-art implementation. Bellman is in Rust, just so you know. So we commissioned this very large instance to build very large circuit, up to 10 million constraints. So you can notice that for relatively short programs, ranging from, so the number of constraints, you can see it as a complexity of a program. Okay, the greater the number of constraints, the more complicated the program, or the longer the program is. Okay? You can see that below 1 million constraints, we are like significantly faster than Bellman, actually. And you might notice that at the end, for very large circuit, so ranging from 1 million constraints, the performance of gnark tends to degrade a little bit. We have identified the problem. Actually, it's for the multi-exponentiation. For the prover, we don't leverage all the power of the CPUs. And it turns out that we found that for 10 million constraints, we only use 30% of the CPUs. And yet, we managed to be 5% faster than Bellman. We are currently working on that. In the coming weeks, we will likely find a solution to leverage all the CPUs, and the numbers will be greater at the end. Okay, so another benchmark, this time on a consumer-grade hardware. So this time the benchmarks are on a MacBook Pro from 2016 with 8 cores, says 16 gigabytes of RAM. We tested it against a 40,000 constraints program. It's not just a random number, it's roughly the size of the Zcash span circuit. And you can see that we still have a significant advantage over the state-of-the-art implementation. Okay, it's roughly 18% of performance improvement. Okay, so how did we manage to get this fast? In parallel to gnark, we needed a finite field library in Go, which didn't exist or wasn't as efficient as we wanted it to be. So we developed in parallel a tool called goff. It stands for Go Finite Field. It's just for ground fields. It does not handle field extensions, okay? It's a command line tool, and basically it generates a code base given a modulus of optimized Go code for a very fast arithmetic library. Just so you know, there is no assembly in here. We use the Go intrinsic functions instead. You can check out our repo. We also have some blog posts, some technical articles about it. Just also, so you know, we also found a nice algorithmic improvement over the state-of-the-art modular multiplications that can be used only for the specific modulus of the curves that we support. Also, we support the 2 BLS curves and the BN256 curve in gnark. Okay, so feel free to check the repo. Okay, so I'm nearing the end of the presentation. What's next? gnark is currently released in alpha version. We are in the process of refactoring and cleaning the code base a little bit. So expect significant changes in the coming days or weeks. According to demand, we will conduct some security audits on the code. Currently, there are no security features at all. It's clearly said in the Git repository. We will keep optimizing the code according to feedbacks, easier the integration process, etc. And work on the documentation and tutorials. Okay, so that's it. gnark was written by Gautam Botrel, Gus Kotowski, and me, Thomas Piellard. We are a research team at Consensus. If you're interested in our work, we invite you to check out the repo and give us a shout. Thank you. Yes?
Thank you, great work. I have a question. I have actually multiple questions, but I'll start with the most pressing one. How are you planning to deal with conditionals?
Yeah. With the DSL, currently we only have the. So you're probably familiar with the select statement from Zcash. Well, you select. It's how we handle it currently. Okay, so this part is not straightforward for users. They have to be aware that they are building a constraint system. So this is one of the parts that would be easier with a DSL, because with a DSL you just write the if statement and all the software is in charge of taking care of how to implement it. Here we just, via our API, we just provide a select statement. Basically you have to write the branches of your if statement. And at the end, you just call the select on the statement. So it's a bit rudimentary. Theoretically, you can do all the stuff that you can do with a standard if statement. The only thing is that the user needs to be aware of that. So this part is not as straightforward as it would be with a DSL. If you check the repo, we have a std folder in which we implemented some examples, some gadget examples. In particular, we have EDSA, multiplication, elliptic curve, arithmetic, and Edward curves. What Zcash called the jub curves. So if you want to know what it's like to code in gnark, you can check those. But yeah, we don't handle if statement in an as easy fashion as it would be with a DSL.
If I may ask you a second question.
Yeah.
How do you think you managed to beat Bellman? So what's exactly you think is more advanced in your solution? And did you measure it against witness generation? It's like, did you take witness generation as a separate step in Profiler, and did you compare that?
So what you call witness generation is actually the instantiation
in Bellman. So like, if I understand correctly, in gnark, when you construct the code and you call solve, you will generate the witness for all the intermediate variables, so the values of intermediate variables for like all down the circuit.
Yes.
In Bellman, this happens during the synthesize, like when you call synthesize, right? And this is actually quite significant part of the time, and this part is not parallelized in Bellman, unfortunately. So I'm curious whether you taking this part into the comparison, or is it outside the comparison?
I think it's since I might check the test again. I think it's inside the comparison. In fact, I'm not sure how Bellman handles the synthesized functions, like how it is implemented under the hood. We do it in a very, like if you want a rank 1 constraint system, you can think of it as a computational graph. Like if you order the constraints correctly, you can execute them, go through them as you would go through a graph, and just with the user input, you can instantiate all the variables. So in gnark, this part is really cheap. It's straightforward, actually. So it might be one of our advantages against Bellman.
And this is parallelized.
In gnark, it's not parallelized, all right? Because you have to do it sequentially, actually. In fact, you cannot parallelize, but it's really cheap. In fact, you just have to go through all the rank 1 constraints and just have to evaluate them. To solve the variables, it just consists of solving just a normal equation with one variable, so it's really cheap. Also, for the why we beat Bellman, I think the main reason is comes from goff, actually. So if you can check, we have a technical blog post explaining goff implementation. It turns out that in the curves that we use, so we use BLS 377, so you might be familiar with this curve from CXZ. We use BLS 381, of course, the Zcash curve, and BN 256. And those curves are defined on a finite field that have the properties that the highest 64 bits chunk of the modulus is not completely set. And it turns out that you can simplify the state-of-the-art modular multiplication with that. You're probably familiar with the Montgomery multiplication. So it turns out that with those special modulus, you can skip a part of this loop that end up with like 14 to 15% improvement over the state-of-the-art algorithm. And actually, those modular multiplications, it's actually the bottleneck of all the zero-knowledge engine. It is called billions of times. It's one of the main reasons. Also, for the benchmarks, so for the small circuits, it might simply come from the Go routines, which are very lightweight and cheap to deploy. Versus in Bellman, they probably, well, they are using thread, I guess, multi-threading. And it's the cost of deploying those threads, the overhead, maybe for our advantages, because we use Go routines. And maybe with many cores, it helps gnark being really fast. But the main advantage comes from goff.
That makes sense. Yeah. Bellman doesn't, like, they use thread pools, so it's probably more from.
Okay. Time for maybe one more, and then we can wrap up.
So I have many questions too. So, which hash functions have you implemented and tested on this implementation of snarks?
Yeah, so currently on the STD folder that I mentioned before, we have a bunch of gadget implementation. We implemented the MIMC functions. Like bother implementing SHA 256. We know now that it's not snark friendly, and there's a lot of research going on how to find snark friendly hash functions.
Poseidon?
No, not yet.
Are there plans to implement all the different hashing functions?
Yeah, according to demand, we'll definitely add more gadgets, specifically those that are snark friendly. It's very not costly to deploy and to implement. So we'll likely implement those in the future, again, according to demand.
Okay. And last, since it is a pure Go implementation, have you tried to build it, cross-compile it for mobile devices like a smartphone, or have you tried to build it as WebAssembly, something like that?
Not yet. No. It's
it should be possible, right?
Yeah, it should be possible. Yes. Again, it's one of the venues of what we can do later, but we didn't look at that yet. But again, according to demand, we might look at those areas more in depth.
Okay, thank you.
Thank you all for coming.
Okay, so we're taking a small break until 12:55. You can grab some lunch, I think, downstairs, and we'll be back.